Welcome to the last video in the gravitation topic. In this video we'll look at the very basic principles of Einstein's theory of general relativity. So we're already familiar with the concept of relative motion, how objects appear to be moving when viewed from different reference frames. So for example, how fast you appear to be going when you're driving at 100 kilometers an hour compared to someone standing still, or compared to someone else driving at 80 kilometers an hour. The topic of relativity is just that. So it looks at events in both space and time, and it analyzes their relative motion, or the relative times at which they occur. And this topic, which is the relativity of time, is something that we'll look at in more detail in the next topic. The relativity that we're familiar with is that of Newton. We can analyze the relative motion of objects as long as we observe them from inertial reference frames. So that is, as long as we observe them from a point of view where we are not accelerating. We also know that the case of an inertial reference frame on Earth is an approximation. Indeed, it's impossible to find a non-accelerating reference frame in our universe, since pretty much everything is orbiting everything else, or everything is accelerating away from everything else. So in this sense, Newton is always an approximation. Using Newton, we can also only deal with objects that are moving at much less than the speed of light. Einstein's relativity was published in two parts. In both parts, it allows us to deal with objects moving at all speeds, and that's right up to and including the speed of light. So the first of Einstein's theory was the theory of special relativity. And in this theory, he deals only with objects in inertial reference frames. And we'll look at that one in the next two topics in more detail. His second theory is the theory of general relativity. And this is the one of interest to us here, and it's his theory of gravitation. So it deals with the more general and much trickier case of non-inertial reference frames, points of view in which we're accelerating. So that's why we can use it for gravitation. Here's just a quick review of the problems with the Newtonian theory of gravitation. When I first discussed these, I glossed over these 2 points. So I glossed over the fact that he couldn't explain instantaneous action of a force at a distance, and also action at large distances. Einstein's relativity at least partially solves these two problems. So the basis of the theory of general relativity is the principle of equivalence, and that says that gravitation and acceleration are the same, or they're equivalent. So as an example of what that means exactly, we'll have a look at our lift problem. So if we have a man standing in a stationary lift on Earth, he'll feel the acceleration due to gravity of 9.8 meters per second squared. And he'll feel exactly the same if we take that lift off Earth, somewhere in space, far away from any gravitational field, and we give it an acceleration of 9.8 meters per second squared. So based on just that acceleration that he's feeling, he'll have absolutely no way of telling which situation is in. So no way of telling whether that acceleration is coming due to gravity or due to some other means. Of course, there are other indicators, such as the lack of light and air, but that's probably a slightly different problem. The second thing that Einstein defines in his general relativity is the idea of space-time. So that's just exactly what it sounds like. It's our three-dimensional space plus the fourth dimension, which is time. And what that means then is instead of dealing with our familiar three-dimensional vector, we are now working with a four-dimensional vector, where the fourth dimension is time. And since in all the vector algebra we've come across, we deal with each dimension individually, then there's no exception here. So adding a fourth dimension just means that our vector equations become longer, but not any harder. So now the main difference between Newton and Einstein. Newton said that gravity is a force between masses. And he said it's equal to gmm on r squared. This caused him problems because he couldn't explain the instantaneous action of that force at a distance, when as far as they knew, the limitation to signal propagation was the speed of light. What Einstein said is that gravity is due to the curvature of space-time. So in Einstein's theory, gravity is not so much a force as a property of the space around a mass. So to better understand what that means, we'll look at the example of two boats sailing to the South Pole. This example has come straight out of the physics textbook by Halliday, Resnick and Walker, for the reason that I think it's an excellent example and I can't make it better. So if we have two ships, We have a red cruise ship starting from Albany in Perth, and we have a yellow old-fashioned sailboat that's starting from Melbourne. From the point of view of each of those ships, so an observer on Earth, they have to sail, both of them, they have to sail directly south. Also from their point of view, they begin some 3,000 kilometres apart, but as they both sail steadily directly south, that distance gets closer and closer until at the South Pole they can tap noses. So from their point of view, there's some unknown force acting to bring them together. So this is the Newtonian view of gravity. If we watch the two ships from outer space, we can see that the reason they get closer and closer is not due to some unknown force, but because the Earth is a sphere. So it curves. This is the Einsteinian view of gravity. So we'll take a fairly typical diagram representing space-time, and we'll divide our space up into a grid. In the Newtonian view, if we pop in our Sun and our Earth and that lovely galaxy directly behind the Sun, then any light emitted by the galaxy will travel in a straight line and is blocked by the Sun. In the Einsteinian view, if we put a mass anywhere in space-time, then that mass causes space-time to curve, so the curvature of space-time. And it's exactly the same kind of thing as what will happen if we put a bowling ball on a trampoline. So the bowling ball will cause the trampoline to bend down. So in this case, if we pop in our Earth and our galaxy, light from the galaxy travelling towards the Sun will then be deflected around the Sun, around this curve, meaning that we can see it from Earth. So if we think again of the bowling ball and the trampoline, if the trampoline didn't bend under the bowling ball, and we roll a golf ball straight at the bowling ball, the golf ball will hit the bowling ball and bounce straight back, and it'll never reach the other side of the bowling ball. But if the trampoline bends, then if we roll the golf ball directly at the bowling ball, what will happen is it will follow the curved path of the trampoline around the bowling ball, and we can catch it again on the other side. And so this phenomenon you've come across before, this is the phenomenon of gravitational lensing. And the result, as you've also seen before, are images like this one, which is the Einstein ring. The last thing that I'd like to discuss is the current state of general relativity. So when Einstein published his theory, he suggested 3 classical tests. They were the precession of Mercury's perihelion, gravitational lensing, and also something called the gravitational redshift of light, which is that light will travel more slowly when it's leaving a gravitational field as it's moving against the gravity. Some 50 or so years later, a 4th test, which was the test of time dilation, was suggested by another physicist called Erwin Shapiro. So each of these tests have been performed multiple times, and they agree with Einstein's prediction to within significantly less than 1% error. So they're in very, very close agreement with Einstein's theory. More recently, there have been several other tests suggested. So the first of these is something called a Null Test. And in a Null Test, they kind of do the opposite. So they take predictions from other theories, so for example from Newtonian theories, as well as from several more recently developed competing theories, and they take predictions which are not predicted by general relativity, and they test those. So in the first set, the classical tests, they're testing to see if general relativity predicts the correct things. And in the second set of tests, this Null Test, they're testing to see whether general relativity correctly doesn't predict things. The second set of modern tests results from the fact that technology has been flying along. The rapid development of the technology has allowed a number of different predictions of relativity to be tested in extreme conditions which weren't available to Einstein. So for example, the effect of gravity at very, very small distances, at atomic distances and under, or things in very high gravitational fields, so around black holes. And thus far, each of these tests has also supported relativity, but often also has supported some of the other competing theories as well. So the thing to keep in mind about science is that all of our theories are based on the evidence that we have, so on what we can see in the world around us, right? And as our technology improves, we have more data to analyze. So when Newton developed his theory, it completely changed the current scientific thinking. It was a major turning point for the way we look at the world. It explained the data that he had at the time. It worked. Its predictions were verified again and again and again. but there was still debate as to how it actually worked. And Einstein's theory is in the same situation. So it's a great improvement on Newton's in the sense that it explains a lot more data on a much larger range of situations. So it explains much more of our world. And it has also predicted a large number of behaviors before the technology was available to test it. So the more tests that we can do of Einstein's theory, the more certain that we can be about its accuracy. So at the moment, Einstein's theory of general relativity is still the best theory that we have for explaining gravity and to predict the effect of gravity. But even with it, we really don't still understand exactly how it is that gravity works. So we get to keep playing.